So usually when you learn the central limit theorem, it's kind of hard to wrap your head around what it's trying to get at. So I have created an experiment to really understand this. So I have a whole course on using Excel with statistics, and I have a free Excel workbook that you can work along. So I'll drop a link to it in the description of this video, or you can go to divideandconquermath.com. This is related to my OpenStax materials. So if you go into OpenStax statistics and look under chapter 7, you'll see the central limit theorem experiment. But otherwise, you can just look in the description of this video for a link to the Excel worksheet. So let's get started. So the premise behind the central limit theorem is that you have to have a lot of data for it to work. So ideally, for this to work, you would have all of the possible data from a population. And so for this experiment, what I have here is height and weight data. And what we are going to pretend here is that I was able to go to some college, we'll call it ABC College, and I was able to magically get all of the height and weight data of every single student. So the amount of data here, so this is student 1, student 2, student 3. So I have here 25,000 different data points from this college. And so for the sake of this experiment, we're going to pretend that that's everybody in the population, which again is something that you usually can't get to. So what we're going to do is we're going to run an experiment to see how the central limit theorem kind of comes out of this using the fact that I have my entire population's data. So the other thing that you want to kind of keep in mind of like where this comes from is that in reality, you can't get probably 25,000 data points, the entire population's data. It's almost always impossible. So the idea is that in reality, I would probably just get a sample, right? So maybe I would survey, say like students 20 through 40. Somehow I randomly collected like these data points. But then somebody else goes and surveys a bunch of people and they would survey, say like 44 through 64. So that would be their data set. So this is something that we understand about sampling is that you can't get the whole population and you're just getting a piece of it. Okay, so let's start going through this. Okay, so the way that this experiment is going to start out is we're going to think about the situation where we send 3 students to go around ABC College and survey 50 students asking for their height. So I have the data that each one of these students collected, and these are, you can scroll down, you can see that these are 50 different data points. So what we're going to do now is we're going to make a histogram for each data set, which we can easily do with Excel. So I'm going to start with student 1. I'm just going to select all of their data, and then I'm going to insert a histogram associated with this. So I go into recommended charts, and I can find a histogram. So here I'm going to rename this. Let's see, I'll rename this as student 1. So there's my first histogram. Let's make a histogram for student 2. Student 2. And make them all the same size about. Okay. And then let's see, this time I think I'll get the title if I take student 3 in there. So let's go ahead and just do this. Nope, still didn't get the right chart title. Oh well. So we'll just rewrite this as student 3 so that they're all properly labeled. Okay, great. So the first thing that we want to notice in looking at these histograms, so we're just trying to notice like what can be said about these. So remember, a histogram is basically taking your data and saying how much data fits into certain buckets. So Excel has gone through and created its own buckets and then kind of dumped the data into there. And if you just look, like if you just do a brief glance at kind of how these graphs are set up. So this bucket is starting at 63.83536 versus this one starting at 63.3211. And this one's starting at 63.39192. So the point here is that we sent out 3 students to go survey 50 students, and So why do they all have slightly different buckets? Because they're all going to have slightly different data, right? And that's what the histogram is showing us, is that I have collected these different data sets and they all look just a little bit different, right? And like, this is not like a perfect like bell curve. This is not a perfect bell curve. This one kind of looks like that. So it's kind of by chance whether or not the data starts to look normally distributed or not, okay? So anything can kind of happen with the data when you're just kind of going out and randomly collecting it. And 50 data points might sound like a lot, but it's actually really not that many in the grand scheme of things. So this is a small set of data that we're kind of working with to get started. Okay, so that's the first part of this. So let's keep going. So we want to start understanding patterns that emerge that move us towards using the central limit theorem. So now what we're going to do is we're going to have 50 students go out, and this time we'll have them get 60 data points, again on height. So what we have underneath here is we have for each student, so I have student 1, student 2, student 3, all the way out to student 50 over here. These are the 60 data points that each student went out and got. And so I think it goes without saying that each student's going to have a slightly different data set, right? That's just like we saw here with 3 students. If you have 50 students, of course they're going to have slightly different data sets. Okay, so where the central limit theorem really starts is it starts with the idea of we should take the mean of each of these data sets. So what I'm going to do is I'm going to take my average formula, and I'm just going to take the average of each student's data. So I go ahead, and so here's the average for student 1. The beauty of this is once you type in one mean, you can just go ahead and drag it all the way across, and you've got all your mean formulas, so everything's calculating. So now we've got the mean for each set of data. And again, it would make sense that each mean is not equivalent to the previous student, right? They're all going to be slightly different because, again, everybody collected slightly different data. Okay, so the central limit theorem asks you to take the mean of all of your data sets and then make a histogram of the means. So I'm going to take all of that mean data and I'm going to insert a histogram. So I've selected all my mean data, come up here to recommended charts, and then I can find a histogram. Okay, so right now this histogram based off of my means doesn't really look like anything too interesting right now, and that's okay. So this is still considered to be a small amount of data. So this is making a histogram off of, once again, 50 data points. And so just like on the previous tab, where having 50 data points doesn't mean you're going to get a normal curve, same thing here. We only have 50 data points, so histogram is going to be what it is. Okay, and so this is kind of the first point of the central limit theorem. For this to work, you need a lot of data, okay? So one thing that we want to start moving towards is, what do we mean by a lot of data, and how does a pattern emerge? So let's move on to the next tab. So now we're going to do the exact same thing, but in this case, now I have an army of students going out and collecting 60 data points. So in this case, I am going to have 1,500 students. So 1,500 students each went out and surveyed 60 students for their height. So I'm going to do the same thing again, where I'm going to take the average of each data set, and let's see, take this, go all the way to the end of my data, and then I'm just going to backfill that formula in all the way over. So now I have 1,500 means, okay? And from here, this is what we're going to make a histogram on. So now we're talking about a lot more data. So let's see what happens now with this histogram. And so this is kind of the point of the central limit theorem. So when you do this enough times, you take enough samples, the way that the means are distributed on a histogram, it will start to emerge as a normal curve. So we saw that when I only had 50 sets of data, so I had 50 means, the histogram didn't look like anything. But now I have 1,500 means, and you can start to see how this is looking like a normal distribution. So let's continue on. So now what I have here is I have, let's see, how many students do I have? This is 5,000 students. So now I have 5,000 students with their data. And I'm going to do the same thing once again. I'm going to write out my means for them. So now I've had 5,000 students go out and survey 60 students. So what does the histogram look like in this case? So once again, I'm going to insert. And now you can see this histogram is now looking smoother and smoother, right? So the previous step, this is looking a little bit more jagged. Now I have 5,000 means to base this off of. This is looking like a normal curve, right? Okay, so let's keep going with this. So what's interesting about this is that it doesn't matter what type of data you use. So I've been using height data, but let's switch this to now the weight data, right? Because we said that we had height and weight data. So we're going to go back to that 5,000 students collecting the 60 students weight each. So I have all these different data sets. And in this one, I've just gone ahead and filled in the means because I think we know how to do that. So we're just going to make the histogram in this case. So now I can see that the histogram for all of this weight data, it also looks like a normal curve, right? And so this is kind of the point of the central limit theorem. It doesn't matter what type of data you use. If you have enough data sets and you take the mean of them, so at this point we had to take 5,000 data sets to get this curve to work out. But when you get to a very large number of data sets, all the same size, and you take the mean of them, the histogram of the means is always going to look normally distributed. So again, this works for any type of data. So what I thought would be interesting is to now take a totally different set of data. So what I have here is data that is uniformly distributed. So let me show you what that means. I'm going to make a histogram of this new data set. This is a data set of 25,000 different points. So let's take a look at what this histogram looks like. Okay, so this is pretty interesting. Hopefully Excel doesn't crash on me. Okay, so here's my histogram of this data. So this is data that's uniformly distributed. So what it means is that any one of these data points is equally likely to happen. So this is how this data is distributed, okay? So there's the histogram. Now, what I've done is, let's say that this is the amount of time that you have to wait maybe for another bus to come. So it's between 0 and 1 minute. So this is like the number of seconds. So let's say we just have buses coming very, very quickly through some terminals. This is kind of a weird experiment, I know. But so it's equally likely that within a minute a bus could come, okay? So let's say that now I have my students go out and my army of students, so I've once again got 5,000 data points here. So let's say that we have students go out and they each wait and see how long it takes a particular bus to show up within the minute. So each one of them is just sitting at a bus terminal and they time each bus and they write down how long it takes between 0 to 1 minutes for that bus to show up. So my 5,000 students have each collected their own data set, and once again now I've taken the means of all of these data sets. So according to the central limit theorem, what should happen is if I take the histogram now of the means, this should be normally distributed. So let's see if that's true. So here's my histogram, and yes, it is normally distributed. So this is what's really wild about the central limit theorem, is that it doesn't matter what the distribution of your actual data looks like. So this data is uniformly distributed. This is what its histogram looks like. when you start taking means of data sets, so when you have collected enough data sets, the distribution of the means always ends up looking like a normal curve. So that's kind of a surprising thing. The other surprising thing is that this theorem also works with proportions. So this is kind of an interesting thing. So now my data is going to be, do you like Star Wars? Yes or no? And once again, I have just 25,000 data points of people who answered this survey of yes or no, I don't like Star Wars. So now what I'm going to do is we're going to pretend that, again, this is my population data. And I have my army of 5,000 students go out and ask 60 people, do you like Star Wars, yes or no? So this is the survey results from all 5,000 of my students. So they asked 60 people each, do you like Star Wars, yes or no? Now, from here, instead of taking the mean, so I can't take the mean of yes or no data, right? There's nothing to take a mean of. But instead, what I can do is I can record the proportion. So what I've done is this is the proportion of people that said yes in each student's survey. So this is 73% of people said yes in the survey, 76% of people said yes in the survey, so on and so forth. Okay, so here's what's kind of crazy about the central limit theorem. So it also works for proportions. So if I take all of this proportion data, let's see, if I make a histogram of it, it's going to look a little funkier in this case, but it still approximates, still looks like that normal distribution, right? And so that is what the central limit theorem says, is that when you have enough data sets and they're all the same size, and again, you're thinking like out to 5,000 data sets, so like more than 5,000 ideally. When you look at the distribution of the means or the proportions for those data sets, it will always look like and approximate a normal function. So from that, we can do a lot of very cool statistics.